Hi, I'm Angel Gulfo and I'm here to report the objective, introduction, and functions of the ALU. So let's start with the objectives. First is introduction to the ALU, functions of the ALU, ALU flags and their purpose, interaction with the control unit, arithmetic operations, logic operations, program flow in ALU, simulation of arithmetic operation, and lastly, simulation logical operations. Let's start with the introduction to the ALU. ALU, or Arithmetic Logic Unit, is a fundamental component of a computer central processing unit, or also known as CPU. It is responsible for performing a variety of arithmetic and logical operations on binary numbers, which are the basic form of data in computing. The arithmetic logic unit is essential for executing instructions and processing data, making it critical part of any digital computer system. Ang arithmetic logic unit ay key part ng computer's Central Processing Unit or CPU. Ito ay responsable sa pag-perform ng basic mathematical calculations at logical operations on binary numbers, which is ito ay fundamental data format sa pagdating sa computing. And ALU, pwede ang ALU kaya niya mag-add, subtract, multiply at divide ng numbers at mag-perform ng logical operations. Ang arithmetic logic unit ay essential sa pag-execute ng instructions at pag-process ng data sa computer system. Crucial din siya sa building block na nakakatulong sa computer system para ma-perform yung calculations tsaka logical decisions na kinakailangan para gumana ang isang program or application ng maayos. Next is the function of the ALU. First is the arithmetic operations. Arithmetic operations performs basic mathematical calculations such as addition, subtraction, multiplication, and division. These operations are crucial for executing mathematical tasks in programs. Arithmetic operations are more focused on mathematical problems or mathematical computations, mga ganun. Next is logical operations. The ALU also handles logical operations, which include comparisons like greater than or equal to, and bitwise operations such as AND or NOT. These operations help the computer make decisions based on the data it processes. Meron siyang kasamang XOR or exclusive na OR. Ito naman ay nagpo-produce ng true output when the inputs differ. So basically, ang logical operation ay nagmamanipulate ng binary data. Thirdly is shift operations. The ALU can shift binary numbers left or right, which is useful for various calculations and data manipulations. More advanced ALUs may use techniques like barrel shifting to perform these operations efficiently. Pag left shift, effective siya kapag nagmumultiply ng number by powers of 2. Sa right shift naman ay nagdi-divide ng number by powers of 2 din. Lastly, comparison operations. By performing logical operations, the ALU contributes to the decision-making capabilities of the computer, allowing it to execute conditional statements and control of the flow programs. So, itong comparison operations ay nagko-compare ng dalawang values para ma-determine yung relationship nila. Tulad ng paggamit ng equal to, which is chinecheck kung yung two values ba ay magkaparehas, greater than, kapag yung isang value ay mas malaki kumpara sa isa. Then less than is checking kung isang value ay mas less or mas maliit kumpara sa isa. And these are the common functions to the ALU.
So next is I will discuss about the ALU flags and their purposes. So arithmetic and logic instruction. Most arithmetic and logic instructions affect the processor status register or flags. As you may see, there are 16 bits in this register. Each bit is called flag and can take a value of 1 and 0. So we have carry flag, zero flag, sign flag, overflow flag, parity flag, auxiliary flag, interrupt enable flag, and direction flag. So first we have carry flag. This flag is set to 1 when there is an assigned overflow. For example, when you add bytes 255 plus 1, result is not in range, or when there is no overflow, this flag is set to 0. So as you may see, there is 16 bits in register and each bit is called flag and can take a value of 1. So in carry flag, um, here, if CF is equal to 1, if there is a carry out from the MSB or most significant bit on addition, or there is a borrow into the MSB on the subtraction, let's see if CF is 0 otherwise, and CF is also affected by the shift and rotate instruction. So the carryout flag is a single bit in the status register of a CPU that indicates whether an arithmetic operation has resulted in a carryout of the most significant bit or the MSE during um, addition or a borrows during subtraction. So the purpose of it is it is primarily used in an assigned arithmetic operation. So for example, when adding two numbers, if the result exceed the maximum value that can be represented, example is 255 for an 8-bit number, the CF is set to 1, indicating an overflow, and this allows subsequent operation to take carry on into account. So next we have zero flag. It is set to 1 when result is 0. So for non-zero result, this flag is set to 0. So in the zero flag, ZF is equal to 1 for a zero result, and ZF is equal to 0 for a non-zero result. If this In this example, the result is not 0, so ZF is equal to 0. So the zero flag is set when the result of an arithmetic or logical operation is 0. So the purpose of it is used to determine the outcome operation. For example, in conditional branching, if the ZF is set, it may indicate that a certain condition has been met. And this flag is crucial for loops and conditional statement in programming. Next is sign flag. Um, it is set to 1 when the result is negative, and when the result is positive, it is set to 0. Actually, this flag take the value of the most significant bit. So here, SF is equal to 1 if the most significant bit of a result is 1. It is mean that the result is negative. If you are giving a sign interpretation, and SF is equal to 0 if the most significant bit is 0. So in this example, the MSB of the result is 1. So the sign flag is equal to 1. So the sign flag, it indicates that the sign of the result of operation, it is set to the value of the most significant bit of the result. So sign flag, the purpose of it is it in assigned arithmetic, if the most significant bit is 1, the result is negative. So if it is 0, the result is positive. This flag is essential for determining the sign of the result, which is particularly important sign integer operation. So next is the overflow flag, set to 1 when there is a signed overflow. For example, when you add bytes 100 plus 50, result is not range. And there is two types of overflow flag, which is signed and unsigned. So the overflow flag is just set when an arithmetic operation produces a result that is too large or too small to be represented in the given number of bits for assigned number. So the purpose of it is it help detect signed overflow condition. For example, when adding two large positive numbers that result in negative numbers will set to OF or overflow flag. And this flag is crucial for ensuring that the integrity of signed arithmetic operation. Next, we have parity flag. This flag is set to 1 when there is even number of 1 bit in result and to 0 when there is odd number of 1 bits. Even if result is a word, only 8 low bits are analyzed. So, if the parity flag is equal to 1, if the low byte of a result has even number of 1 bits, it is an even parity. So, if the parity flag is equal to 0, otherwise it is an odd parity. So, the parity flag indicates whether the number of set bits 1 in the result is even or odd. So, the purpose of it is used in error detection schemes. So, if the parity flag is set, it means there is an even number of 1 bits, which can be used to verify data integrity. So this flag is particularly useful in communication protocols and memory check. And next we have auxiliary flag. So set to 1 when there is an assigned overflow for low nibble or 4 bits. So if the AF is equal to 1, if there is a carry out from bit 3 on addition, or there is a borrow into the bit tree on subtraction. So if the AF is equal to 0, otherwise AF is used in binary coded decimal or BCD operation. So auxiliary flag is used to indicate a carry or borrow from the lower nibble, the lower 4 bits of the arithmetic operation. And it's primarily used in binary coded decimal or BCD arithmetic, where operation on decimal numbers are performed in binary. And the auxiliary flag help manage operations that require adjustments for BCD representation. Next is we have interrupt enable flag. When this flag is set to 1, CPU reacts to interrupt from external devices. The interrupt enable flag controls whether the CPU will respond to external interrupts. So the interrupt enable flag um, controls whether or not CPU will respond to external interrupt. And its purpose is if the interrupt flag is set to 1, the CPU can respond to interrupt from hardware devices like keyboard, mouse, etc. If it's set to 0, it interrupts are disabled. So this flag is very important for managing multitasking and real-time processing in operating system. And next is direction flag. So this flag is used by some instruction to process data. When this flag is set to 0, the processing is done forward, and when this flag is set to 1, the processing is done backward. So, in the direction flag, it determines the direction in which string operation are processed, and the primary purpose of it is when the direction flag is set to 0, the string operation like copying or comparing string process data from low memory address to high address or forward. When set to 1, they process from high to low or backward. And this flag is important also in optimizing string manipulation operation in assembly language and low-level programming. So next we have here how the ALU interacts with the control unit. So the ALU operates in conjunction with the control unit rather than independently. to execute instruction and oversees data flow within a computer. Um, so here's the summary of how ALU collaborates with the control unit to carry out its function. First, we have instruction flow. The control unit transmits instruction to the ALU using binary control. So the control unit is responsible for directing the operation of the CPU. It sends instruction to the arithmetic logic unit or ALU in the form of binary control signals. And these signals specify what operation the ALU should perform, such as addition, subtraction, or logical operation. And the binary format allows for precise communication when the control unit and the ALU and ensuring that the correct operations are executed based on the program instruction. And also operation execution. The ALU carries out the operation defined by instruction, retrieving data from registers or memory, and processing the data according to the control signal, which may involve arithmetic, logical, or shifting operation. So once the ALU receives the control signal from the CU, it executes the specified operation, such as retrieving data. In retrieving data, the ALU fetches the necessary data from register from the smallest past storage location within the CPU or from memory which has large storage than that holds data and instruction. And the control unit ensures that the correct data is made available to the ALU. And processing the data, the ALU processes the retrieved data according to the control signals. This processing can involve various types of operation, such as arithmetic, logical, or shift operation. And we have also result storage. The ALU outputs the result of its operation to register for registers for immediate access, memory for long-term storage, and update status flag to reflect conditions such as overflow or zero result. So after the ALU completes its operation, it outputs the result in several ways. In register, the result is often stored in registers for immediate access by the CPU, and this allows for quick retrieval and further processing without needing to access slower memory. And if the result needs to be saved for later use, it is written back to memory. This is essential for maintaining data persistence beyond the immediate operation. Um, and the ALO also updates status flag based on the result of the operation. This flag indicates specific conditions such as overflow flag, zero flag, send flag, carry out flag, as I discussed it earlier. So, in program control, the ALO and control unit collaborates to oversee the execution of the program by identifying next instruction, making decision based off the status flag. And as the ALO and control unit work together to manage the overall execution of the program, after execution of the current instruction, the control unit determines what next instruction should be, and this involves fetching the next instruction from memory and then coding it to understand what the operation is required. And as the control unit uses the status flag updated by the ALU to or ALU to make decision about the program flows. If the for example, if the zero flag is set, indicating that the result of the last operation was zero, the control unit might branch to different part of the program, and the decision-making process is crucial for implementing control structure like loops and conditional statement, allowing the program to respond dynamically to different conditions. And that's all.
So our next topic is about arithmetic operations. But first, let me tell you about arithmetic logic unit. Arithmetic logic unit is a fundamental component of the CPU, responsible for performing both arithmetic and logic operations. Arithmetic operations include basic mathematical functions like addition, subtractions, multiplications, and divisions, while logic operations involve comparisons such as AND or AND XOR. The ALU works closely with the control unit, which sends instructions to the ALU telling it what to do with the data. So, in terms of arithmetic operations, the ALU can perform basic mathematical functions like addition, subtractions, multiplication, and division. These operations are crucial for almost all types of computing tasks, from simple calculations in everyday software to complex computations in scientific programs. The ALU ensures that these operations are executed efficiently, enabling the CPU to perform a wide range of tasks. So let's focus on one of the basic operations performed by the ALU, the add operation. The add instructions takes two operands, adds them together, and stores the result in the first operand. For example, if we have add ax, bx, the ALU will add the value in bx to ax and store the result in ax. This is how the ALU handles addition in the CPU. Here's an example of the add operations. Let's say ax is equal to 100 and bx is equal to 50. Performing add ax, bx results in ax is equal to 150. The flags would be updated as follows. Carry flags, 0. No overflow. 0 flags, 0. Result is not 0. Sign flag, 0. Result is positive. Overflow flag, 0. No sign overflow. This example shows how the add operations works and how flags provide valuable information about the result. The add operations follows a clear process in the ALU. First, fetch the operands. The ALU receives the operands to add, which could be in registers or memory. Second is perform the addition. The ALU adds the two operands together. Third is store the result. The result of the addition is stored in the first operand, which is AX. And fourth, update flags. Based on the result, the ALU updates the relevant flags to indicate overflow, zero result, etc. Besides add, the ALU performs other arithmetic operations including subtractions. It subtracts the second operand from the first. For example, AX BX means AX is equal to AX minus BX. In multiplication, it multiplies two operands. For example, AX BX means AX is equal to AX times BX. And in divisions, it divides the first operand by the second. For example, AX BX means AX is equal to AX divided by BX. So these operations are equally important and follow a similar process to the add operations, affecting the flags and allowing the CPU to perform necessary computations.
So, without before we discuss about the arithmetic logic unit, ALU. So, in my part, I will tackle with logic operation. So, it's a simple rules that help computers work with binary numbers made of zeros and ones. The ALU use this operation to solve problems, make decisions, and process data. It's also the core part of computer function, ensures smooth program flow and efficient data handling. For example, a task include checking conditions like yes or no, modifying data, and performing simple math. So these are common logic operation and not is not NAND. So first one the logic operation. is returned true if either input is true. In computer programming, it's written as 2 ampersand. In Boolean algebra, it's written as AB for two inputs A and B. Include two table and circuit diagram. So this one is circuit diagram and this one is two table. So I will explain how it works in two table. So for the first row, when both input A and B are 0, so with the AND operation result is 0 because the condition for the output to be 1 is not met. Both input need to be 1. The second row, when input A is 1 and input B is 0, so the result is 0 because the condition for the output to be 1 is not met. Both input need to be 1. The third row, when input A is 0 and input B is 1, so the result is 0 because the condition for the output to be 1 is not met. Both input need to be 1. The fourth row, when both inputs A and B are 1, so the result is 1 because the condition for the output to be 1 is met. Both inputs are 1. Next one is our logic operation. So it's returned true if either input is true, output is false. If all inputs are false, usually written as 2 of that in computer programming, our value in Boolean algebra A plus B. So remember that do not mistake the operation for the arithmetic addition. Even though they both use the plus symbol, they are distinct operations. So for this one, I will explain how it works in the truth table. So for the let's remember the operation evaluates to true one if at least one of its input is true. It only evaluates to false 0 if both input are false. So row 1, both A and B are 0. Since either is true, the result A plus B is 0 false. Row 2, A is 1 and B is 0 because at least one input is 2, so the result A plus B is 1, 2. Row 3, A is 0, false and B is 1, 2. Again, since at least one input is 2, the result A plus B is 1, 2. Row 4, both A and B are 1, 2. Since at least one input is 2, the result A plus B is 1, 2. Next one is not logic operation. Return to if input is false, false if input is true. Usually written as in computer programming in Boolean algebra, not value is A overscore with overscore. So I will also explain how it works in table 2. So for the row, so let's we remember the two table for not operation is inverse the input signal if the input is 2, 1, so, and the output is 4, 0, and vice versa. So for the first row, if the input A is 0, then the output of the NOT operation will be 1. Row 2, if the input A is 1, then the output of the NOT operation will be 0. Next one is AND logic operation is returned to if input are false. False if either input is true. Input auxiliary is will write like AP over Scott. This is a simple of that. AND is one of two universal logic gates allowing creation of logic operation using only AND gates. So for the table 2, row 1 when both inputs A and B are 0, so the end result A and B is also 0. So the NOT operation on this result give us 1. Row 2 when A is 1 and B is 0, the end result is 0 and the NOT operation on this result give us is 1. Row 3 when A is 0 and B is 1, the end operation is 0 and the NOT operation on this result gives us 1. Row 4 when both inputs A and B are 1 and the operation results is 1 and the NOT operation on this result gives us is 0. Next one is NOT logic operation. Return to if input are false. False if either is true. Input auxiliary, so they will write the A plus B over Scott. NOT is the one of two universal logic gates. So for the table 2, for the first row, the NOT operation is the negation of the R result. Since 0 plus 2 zeros plus 2 is 0, the NOT of 0 and 0 is the opposite, which is 1, so the output is 1. The second row, the NOT operation negates the R result. Since 1 plus 0, 1 plus 0 is 1. So the NOT of the 1 and 0 is the negation of 1, which is 0. So the output is 0. The third row, the NOT operation negates of R result. Since 0 plus 1, 0 plus 1 is 1, so the output is 0. The fourth row, the NOT operation negates the R result. Since 1 plus 1 plus 1 is 1, so the NOT of 1 and 1 is the negation of 1, so which is 0, so the output is 0. So summarize that the NOT operation only gives the true one output when the both inputs are false 0. For all other inputs combination, the output is false 0. The next one is XOR logic operation. Is returned to if inputs difference false if they are on the same. In the Boolean algebra is write like that. Plus sign inside the circle. Next, I will explain the two tables. In the first row, when the both input are 0 and so the XOR operation result in 0 because the input are the same. The second row, when the one put is 1 and the other is 0. So they give the result is 1 because the input are different. In the third row, similar to the second row, when the one put input is 0 and the other is 1, so the result is 1 because the input are different. Fourth row, when the both input are 1, so the result will be 0 because the input are the same. Summarize as XR operation give the true one output when the inputs are different. For identical input combination, the output is false is 0. Next one, the XNOR logic operation return true if inputs are the same, false if they different, output is false if input are the combination of true and the false, output is true if input are the all true or false. So this one is the Boolean algebra represent the XNOR value. So for the table two, for the table tools, first row, since both input as 0, the result will give the 0 because it negates this result, so final output is 1. The second row input are different, 1 and 0, so the result is 1. So the result is 1. The third row, the input are also different, 1 and 0, so the result also give the final boost is 0. The fourth row, both input are 1, so the result will give in 0. The XNOR operation negates this result, so the final output is 1.
Hi, my name is Giuseppe Cedric, and my topic for today is program flow in ALU. Program flow in ALU. What is program flow? Program flow refers to how a program controls the sequence of its execution. It determines which instructions are executed and in what order, enabling decision making and repetitive processes in programs. The role of ALU in program flow, the arithmetic logic unit, is crucial in program flow control. It executes operations, performs arithmetic like addition, subtraction, and logical and or operations. Evaluate conditions like update flags, special indicators like zero flag and carry flag to indicate the outcome of operations. Support control structures, guides, jump loops, and other program decisions based on the flag statuses. Key components involved: flag register. Flags are special indicators in the processor that shows the result of the last operation. Key includes zero flag, set to 1 if a result is 0, indicating equality or zero outcome. Carry flag, set to 1 for unsigned overflow, meaning the result is too large to fit. Overflow flag is set to 1 for signed overflow, signaling that the result exceeds the range for its signed numbers. Program counter holds the addresses of the next instruction to execute, updated during jumps or function calls to redirect the flow of execution. Stack pointer tracks the stack during program execution, saving and restoring the program state for functions calls and return. Types of program flow. We got unconditional jumps. It directly transfers control to a specific part of the program. This example shows the program can jump directly to a specific part of the code labeled as label. After the jump, the program resumes execution from that point. Conditional jumps depends on flag statuses set by the ALU. Examples include jump if equal executes if ZF is equals to 1. Jump if greater executes if a sign comparison shows greater. The CMP instruction checks if the two values in AX and BX are equal. It does not it does this by subtracting BX from AX without saving the result. If the result is 0, the 0 flag is set to 1, which means the two values are equal. The program then jumps the label equal and executes code there. It executes code there. If the ZF is not set, values are not equal. The program moves on to the next instructions after CMP. Loops repeat sections of code using counters and conditional jumps. The MOV instruction sets the loop counter CX to 5. The program executes the code inside the loop and uses the loop instructions to decrease CX by 1. If CX is not 0, it jumps back to loop start and repeats the process once CX reaches 0, and then the loop ends. How ALU manages program flow. Condition evaluation, instructions like CMP using the ALU to subtract two values, the result updates flag like zero flag and carry flag to guide program decisions, and decision making instructions like jump if equal and jump if not 0 use the updated flag values to determine whether to continue sequential execution or to another part of the program. Arithmetic in loops. The ALU manages loop counters, CS register, decrements them, and checks conditions to decide whether to repeat the loop or exit. The interaction with control unit. The ALU outputs, such as flag statuses, guide the control unit in modifying the program counter PC. This ensures dynamic execution based on conditions. Examples in assembly, we got simple jump. This example demonstrates an unconditional jump where the program skips directly to the label next. The MOV instruction sets the AX register to 5, and the ADD instructions adds 2 to AX. Once the program reaches next, resulting in AX is equals to 7. conditional jump, the CMP instruction checks if the value in AL5 is equals to 5. Since they are equal, the zero flag is set to 1, and the GE instruction it causes the program to jump to the label equal, where BL is set to 1. If the value were not equal, ZF would remain 0, and the program would instead set BL to 0 and continue to end. Now we got loop. The MOV instruction sets the CX register counter to 3. The loop instruction decreases CX by 1 after each interaction or iteration as long as CX is greater than 0. The program jumps back to loop start to repeat the code, and when CX reaches 0, the loop ends. The key insights. The ALU plays a critical role in controlling program flow through operations, condition evaluations, and flag updates. Flags PC and SP enable branching, looping, and subroutine execution effectively, and understanding how the ALU interacts with control instructions ensures efficiency and logical program design.
Good morning, everyone. My name is Angeline Lucine, and we're going to talk about the simulation of arithmetic operation and simulation of logical operations. So, let's go back to simulation of arithmetic operations. First, we have the addition, which means it adds two values. For example, add AX and BX adds the values in registered AX and BX, storing the result in AX. So, now we have a given of AX is equal to 5, BX is equal to 3, and we're just going to simply perform a addition. So AX is equal to 5 plus 3, which is 8. Now the value is stored in AX registered with 8, which is the 8. Second, we have subtraction. So it means subtract one value from another. Example, sub AX, BX subtracts BX from AX, storing the result in AX. So AX is equal to 8, BX is equal to 3. Just subtract the value of 3 to 8, which is 5. Now we have the value of 5 stored in the AX register. Next, we have comparison. Comparison means subtracts two values but doesn't store the result. It only updates flags for decision making. So example, comparison AX BX checks if AX is equal greater than or less than BX. So if AX is equals to 5 and BX is equal to 3, the instruction performs AX minus BX, but it does not store the result. Instead, it updates the flag to indicate the relationship between AX and BX. So we have an outcome of AX is equal to BX. The program would jump to the label greater. So how does it happen? So how to use a comparison? After comparison instruction, we typically use conditional jumps based on the flags. So JE means jump if equal. So for example, if ZIF is equal to 1, just simply jump to a label, and JG, which means jump if greater, if SF is equal to 0 and ZF is equal to 0, you will just jump. JL means jump if less. If SF is equal to 1, just jump. So for example, for our sequence, comparison AX BX. So we're going to compare the AX, which is equal to 5, with BX is equal to 3. So that's why 5 is greater than BX. That's why the outcome is, so the program would jump to a label greater. Okay. Now simulation of logical operation. So first is AND. This perform a bitwise AND between the contents of register AL and BL storing the result in AL. So for example, move AL 11001100 and load AL with binary 11001100. Move VL 10101010B, load BL with binary 10010101010, and ALBL is we're going to perform an AL and BL result in 100100B. Okay. Next is the OR. This performs a bitwise OR between AL and BL, storing the result in AL. So we have a load for AL, which is 11001100, load BL, which is 10101010. So we're going to use OR, which we're going which will result in 11101110B. Next is the SOR. XOR. This calculates a bitwise XOR exclusive OR between AL and BL with the result stored in AL. For example, we have load AL with binary 11001100 and BL with binary 10101010. So if we're going to perform SOR exclusive OR, it will result in 01100110B. For logical operations, we also have the CMP. So the CMP instructs subtracts BL from AL for comparison without storing the results, same as the arithmetic operation. It only updating flags. The JE instruct jumps the label equal if the zero flag is applied, meaning AL is equal to BL. So same as our first, same with our given in arithmetic operation. So if we have AL with load 25 and BL with 25, comparing AL to BL, we jump to equal label if AL is equal to BL, because we have the same value, which is the 25. Okay. And that's all for our lesson. Thank you.